All right, bear with me today. We're going to talk about how derivatives affect the shape of a graph. These are long notes. I'm going to fly through it. Feel free to pause, rewind, whatever you need to do to be able to get all the notes taken. So, the first one is the increasing-decreasing test. And it's somewhat common sense. It says if f prime of x is greater than 0, this means the slope is positive. If a function has positive slope, then what is it doing? Increasing. If f prime is less than 0, meaning the slope is negative, then the graph is decreasing. Example 1, find all the intervals of increasing and decreasing in the function f of x equals x cubed minus 27x. So, here's what we need to do. We give you the steps here a little bit. Find the derivative, 3x squared minus 27. Determine the critical values, which means we need to set that equal to 0. Factor it. So our critical values are 3 and negative 3. Now, we need to test some values between here. If we test, say for instance, a number in this section, negative 4, we get a negative times a negative times a positive, which is a positive. Meaning that portion of our graph from negative infinity to negative 3 is increasing. Say we plug in 0, we get a positive, a negative, a positive. So, decreasing. Positive times a negative times a positive is a negative. That's why we know that's decreasing. If we plug in a 4, we get a positive, and a positive, which works out to be a positive. So, increasing and decreasing, we know that this graph is increasing from negative infinity to negative 3 and from 3 to infinity. Decreasing, where it's negative, from negative 3 to 3. If we find a couple values, we can sketch a possible graph. f of negative 3 is equal to negative 54. No, positive 54, sorry about that. f of 3 is equal to negative 54. So if we plot those, we get negative 354, 354. We know that it's increasing to that point, decreasing between, and increasing after. Not a real detailed graph, but that is roughly what this graph looks like. Moving on to another example, find the intervals of increasing and decreasing in the function f of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 5. We don't have to sketch it this time. We do need to find the derivative. Minus 12x squared. So the derivative is 12x cubed minus 12x squared minus 24x. We factor, pull out our 12x. We have x squared minus x minus 2. That is equal to 0. Our critical values are 0, 2, and negative 1. So there's our critical values. Now let's test a value to the left of negative 1, like a negative 2. We'd get a negative times a negative times a negative, which is a negative. We test a negative 1/2. We get a negative, and a positive, which is a positive. Test a 1. We get a positive, negative, positive, which is a negative. Test a 3. We get a positive, 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 which is a positive. So, this graph is increasing from negative 1 to 0 and 2 to infinity, and it's decreasing from negative infinity to negative 1 and from 0 to 2. Keep in mind, if you're looking at the increasing and decreasing up here, it will not always go negative, positive, negative, positive. There are times when you will have 2 negatives in a row or 2 positives in a row, so don't get in the habit of finding the first one and just making up the rest. Now the first derivative, first I want us to sketch tangent lines at all these selected points below. So if we sketch a tangent line, and these are real rough, but you get the idea. There's our tangent line. We know, if C's in the middle, that this is increasing and then decreasing. C's in the middle, it's decreasing, then increasing. C's in the middle, it's increasing, then increasing. C's in the middle, it's decreasing, then decreasing. So, suppose that C is a critical number of a continuous function. If f prime changes from positive to negative, like it does at A, if f prime changes from positive to negative at C, then f has a, what is this? Well, it's a maximum when your first derivative changes from positive to negative. For B, when it changes from negative to positive, like it does here, we know that it has a minimum. Now, C pertains to C and D. If there is not a sign change, then there is not a local max or a local min at C. Table 3 says find the local max and local minimum values of the function g of x equals x plus 2 sine of x. So, first thing we need is g prime. 1 plus 2 cosine x. We got to set this equal to 0. And we find that cosine of x equals negative 1/2. Where is that true on our unit circle between 0 and 2 pi? X equals negative 1/2 at 2 pi over 3 and 4 pi over 3. If you don't remember your pi plate, spend a few minutes refreshing that. Once I notice you don't remember, I'm going to start giving pop quizzes over it. So, there is our two critical values. Okay, at 2 pi over 3 and at 4 pi over 3. And really, our number line only has to go from 0 to 2 pi because they gave us endpoints. So, let's check a number between 0 and 2 pi over 3, like pi over 2. We plug it in here. Pi over 2 has a cosine value of 0 times 2 plus 1 is a positive value. Now, between 2 pi over 3 and 4 pi over 3 is pi. We plug in a pi. Cosine of pi is negative 1 times 2 is negative 2 plus 1 means it's a negative value. And between 4 pi over 3 and 2 pi is 3 pi over 2. Plug 3 pi over 2 in, we get 0 for cosine times 0 for cosine times 2 plus the 1 gives us a positive. So, let's talk about this. We need to find a max and a min. A max, a local max, is where it changes from positive to negative. So that's going to happen at 2 pi over 3. And actually we're talking about g, sorry, at g of 2 pi over 3. And the y value when you plug pi over 3 into g is 2 pi over 3 plus radical 3. The minimum, our local min, where it changes from negative to positive, is going to happen here at 4 pi over 3, which when we plug 4 pi over 3 into our g function, x plus 2 sine of x, we end up with 4 pi over 3 minus radical 3. Moving on. Concavity. Let's sketch some tangent lines. I want you to sketch 3 of them on this. So, we've sketched them. Now let's talk about this for a second. If a graph of f lies above all of its tangent lines, like this, on an interval I, then it is called concave up. Depending on what a curve starts and ends. This isn't always true, but concave up is a curve like this, where it could maybe catch water, if you know what I mean by that, but it might not be enough to actually catch water. If the graph lies below all of its tangent lines, that's called concave down. And concave down looks something like an upside down U. So that's concave down. All right, so if we pause this video for a second, decide for me where this is concave up and where it's concave down. Check your answers here. If you have questions on this, please come with them tomorrow. Concavity test. If f double prime of x is greater than x for all x in I, then the graph of f is concave up. So when our second derivative is positive, it's concave up. When f double prime is positive, it's concave up. When f double prime is negative, it's concave down. So let's talk about this. First, they want us to discuss a couple things. Local maxes and local mins we can find first by finding the second derivative, critical values of 0 and 3. If we look at our graph, before 0 it's decreasing, between 0 and 3 it's decreasing, and after 3 it's increasing, which means we only have a local min at x equals 3, the point 3, negative 27. No local max. Now, when it comes to concavity, we need the second derivative, which would be 12x squared minus 24x. We end up with a GCF of 12x, and our critical values are 0 and 2. If we plug a negative number into 12x times x minus 2, we get a negative times a negative, which is a positive. If we plug in a 1 between 0 and 2, if we plug in a 1, we get a positive times a negative, which is a negative. And if we plug in a 3, we get a positive times a positive, which gives us a positive. So that tells us that this graph is concave up from negative infinity to 0 and from 2 to infinity, and is concave down from 0 to 2. One last thing, a point of inflection, P, on the curve is called a point of inflection if the curve changes from concave up to concave down or concave down to concave up. So, how do we find the point of inflection? If you look back, you want us to find the point of inflection at example 4. Look at example 4. If you notice on this graph that it changes at 0 and at 2, then we know that our points of inflection occur when x equals 0 and when x equals 2. And we could, if we needed to, they're not necessarily asking for it, find that those y values using our original function. So, graph f of x equals x cubed, we know what that looks like, or you should. Looks something like this. Where does it appear to have a point of inflection? Well, at 0, 0, we think is our point of inflection, which we can abbreviate by POI. Algebraically, we need the second derivative set equal to 0, so we get our critical value of 0. If we plug a negative number into 6x, we get a negative. If we plug a positive number into 6x, we get a positive. So we find from our graph that our point of inflection actually is at 0 because it does change. Sometimes your second derivative will equal 0, but it won't change values, so it's not a point of inflection. Finally, the second derivative test. This is a kind of important one. If f prime of c equals 0, and the second derivative is greater than 0, then it has a local min. Because if it has a slope of 0, but it's concave up, it's going to look like this. And that's going to be a local min. If it has a slope of 0, but it's concave down, it's going to be that point, which makes it a local max. Now, take a second. On this example, find intervals of increasing and decreasing, locate your local maxes and mins, your intervals of concavity, your points of inflection, and then sketch the graph. Complete this before tomorrow. We will talk about it in class.